Swayam Prabha. Digital India. Educated India.
So I yesterday taught you something on this little bit of magnetic properties of some inorganic complexes in general. So did you realize anything from there? Do you have any question? I didn't teach a lot. I only taught the very basic and tried to give you the general feelings and the concern and the why you should do that. So and that is a basis. If you understand that one, then there are many concepts on the based on that. So this is the basis of something, then it will build up. Okay. So if you have problems, if you do not study, then next classes will be problem. So did you look at least what I taught? What are the concept? What was new? Where you have to think something? No? Any questions here? No. Okay. So I'll slightly recapitulate what I taught yesterday. So first we taught that if you have a one unpaired electron, the unpaired electron is actually spinning, okay, around its own axis, and then also it is rotating around the nucleus. So when you have a nucleus here, and this is nucleus positively charged, and positive charge depends upon how many protons and neutrons, other things are there, whatever they have, mostly protons, and you have the electrons outside, and there could be not one, there are many more sub cells and all are there, and these electrons when they move around, they are moving of their own, and it's not a circular path, or it's not a like what do you call it, peaks trajectory. It can go anywhere. Okay, it has a, it's like a, if you ask a fish to swim in a controlled manner, it cannot. Okay, its space is like just imagine, the physics always need a model. So if you put a fish tank and put a fish and ask him to only follow one path and rotate, it's very hard for the fish to memorize and rotate. Okay, it should be controlled by someone. So in the fish tank, it has the freedom to anyway anyhow to move all around. So you can try to see the trajectory. It can spin in certain corner, certain places more time, but it can go anywhere at any time. Okay. So similarly, when you have electrons, so it is like in the center of this one, and it can zip all around, and it will be like just moving all around in any way. Okay, you have no control. So what is the control they have? The nuclear, this positive charge and negative charge, say they have some kind of electrostatic interaction, and line of forces are there connected. So they will control, but it's like if you take a dog for a like morning walk, you have a length, but you cannot really control the same length all the time. It will take you some to your side, you can take this side. So it's keep on, it's a kind of affair between these two, this side, that side, okay, plus minus. Okay. So when you put energy, the electron goes a little bit far because it gets more excited and all, and so momentums are higher, and then length it goes little bit up, but so, and sometimes you cool it, it comes little bit closer, all sorts of things happens. Okay, you see, how do you see, sir? Yes. So when you make the metal complexes or something, we see the on cooling bond length can slightly shrink, and on heating it can be little bit high temperature, it can be little bit expanded. So you can collect the extra data in both the temperature, and you can see that. Okay, cell volume, unit cell volume also shrinks and expands depending on the temperature. Okay, so now if you have this one, now when you have electric field and a charged particle is moving, okay, then it produces magnetic field around it perpendicular all the time. So this is electrons are like this going on, and you have a, so electrons are everywhere, like somewhere here, like zipping like that, and magnetic field is perpendicular. So when Faraday and Humphrey Davy, they are doing the experiment, the conversion of potassium hydroxide to potassium metal electrochemically. Okay, that's how the first time Humphrey Davy was making potassium, sodium, this metal from their alkali hydroxide, and they had to produce put lot of voltage and then lot of current. So the electron goes and deposits the what do you say the metal on the electrodes, and that time perpendicular they are putting some for some other measurement, some magnetic some small magnets, and they are getting deflected whenever they are passing current or switching off, switching on. So from that means this is always comes perpendicular. So magnetic field, electric field, always they are perpendicular to each other. It's like my hands will be always perpendicular to my this axis of my body. Okay, okay, and you can also put parallel, but for them it is always perpendicular. Okay, so here they will be coming like that, and this is what, because of these electrons moving in an electric field, it will create magnetic momentum. Okay, and you have to have unpaired electron. If you have another electron which are pairing up, then its motion is cyclic wise. Suppose this is anti-clockwise, other than clockwise, they will create the other way around. So their momentums will be cancelled. So one is like polarized light, one is rotate the plus direction, other will rotate minus direction, or will have zero optical polarity, right? Similar way. Okay, now when you have this one, so the magnetic momentum for free electron we calculated to be 1.73 Bohr magneton. Okay, if you convert to chi t, it will convert to 0.375. Okay, this is the value you should remember forever. Okay, now I said that if you have one electron now, its magnetic momentum will be, so it is like S equal to half, and I gave you a formula which is chi t equal to n beta square g square, okay, by 3k. So this is the Boltzmann constant into s plus 1. Okay, this is the s which is we are putting the ground state spin. Now if you have two electrons which you have can have s equal to 1, and that time I mean that it's a triplet. It means two electrons are completely coupled, they are not interacting, it's not like that, they are coupled and they are always together up. They will be tilting but always together in the same fashion. It's not independent of each other. Okay, so when you have nickel, this is a case of copper 2 plus or vanadium 4 plus. Okay, or this will be case of nickel 2 plus and other iron, wherever you have two unpaired electrons on the metal center. Okay, so that time if you put s equal to 1, you get this is a 0.375, it will become 1.01, something like that. So if you go to 3 electron same system, is like cobalt 2 plus, okay, and s equal to 3 by 2, you get this value will be coming 1.87 like this. Okay, so if you keep continuing like that, so if you go to now cobalt, now instead of the manganese suppose 4 plus 3 plus, if you go in a 4 electron system, now this value goes to 2, okay, sorry 3. Okay, so these are for, you can remember that here you have one electron, two electron, you can see the values are not just double, it is more. Okay, that you should remember, mind it. Now here if you go to here to just two, here 2 electrons, here 4 electrons, value you see it is 3 times. So it is nearly going 3 times, okay, when you are doubling it. And here you can see that values are going on. So if you go to manganese 2 plus, it will go to I think 5.47 or something like that, or 87, something like that. Okay, so it has 5 by 2 electrons. So on the gadolinium we have said gadolinium has 7 electrons, 3 plus, it is 7 by 2, and it is 7.87 like that, right? To the value. So you see that I have just 7 times the electron, the value you see how many times. So when you keep one electron and then other electrons away, and they are producing less magnetic momentum. Why? Because they are randomized and they are thermally randomized, and they are not all going parallel to the magnetic axis when you are applying magnetic field, z axis along the magnetic field, and our measurement is along the z axis where the along the applied magnetic field. So those who are orienting little bit perpendicular, they will be giving zero effect. So though they are spin, but they will not give any effect. If they tilt smaller, they give more effect. The more they tilt, they give less effect. And then they, after the 90, the more they tilt opposite direction, they will try to decant from the others. So it's like some of you are trying to make a one kind of a treasure box where you want to accumulate some money and want to distribute to the poor people, and you see some of you are putting back, some of you are actually taking and going for somewhere to gather more, but those expenditure are actually reducing your fund, right? So that's how it is also happening. So when we are measuring in one center all spins are there, they are always parallel to the applied magnetic field. But if you use the same number of electrons, or if you think that, so this is gadolinium 3 plus cannot be equivalent to 7 copper 2 plus. Okay. Why? Because these spins are 7 and they are randomly oriented, hard to control like they are in one place. So what happens if you couple them all them strongly and ferromagnetically very strong, that time this will be equivalent to this, remember this. So when they are coupled completely very strongly, J value is very highly positive, then they will behave like a one gadolinium center, not before that. At what time it happens? If you can happens only in the molecular cluster at very low temperature, below 10 Kelvin. Okay. So where this, if you have copper gadolinium system and they couple, copper recouple, maybe low temperature you can produce such kind of, say this is the area where you can produce this. Below that one they are coupling and they are till paramagnetic, all the spin states are there, that we have shown are there. So this is the meaning of keeping the electrons coupled, uncoupled and weakly coupled. Okay, so you should mind it. You have never thought of these ions, how they behave, how they are equivalent. You have calculated for these ions magnetic momentum, but never you thought on this way. But that's how they behave on the magnetic field. Now, now if I try to probe them, okay, with the EPR spectroscopy, okay. So what you are calling EPR, okay. Now you say that, sir, why do I need to have EPR spectroscopy after the magnetic the classes? Okay. Now it's like if you have to drink water, you are thinking you are drinking the water, right? So is it pure water you are drinking? Are you sure? It's 100% pure, nothing else is in it. What is there? The can water there, the one I am drinking, what are there inside? Can you tell me? Hmm? What happens if I take this water and boil into other side, condense, boil it, it paper condense, then I drink this water, and what will be the difference? Same water I am drinking after boiling, without boiling. So if you go to our bathroom, take the same amount of water, also boil, okay, and drink. Is the same. So when you boil it out, it only the water molecule comes. What we get from the water is actually not only water molecules. Actually, we are thinking this way we are living, but all the time among the water, with the water molecule you have actually inorganic ions, and those ions are maximum what are there. No, if you test this out, I tested out. It has, if you take 1 liter of water from this our bathroom, it has 500 milligram of 500 milligram to say 600 or 700 milligram of inorganic ions, that is mostly calcium and magnesium major. They are nearly 200 milligram to 250 milligram, okay, per liter are there. So basically those are the ions we need for our body, for our bone. If you are drinking this is very pure water, means this is distilled water, and it is in this 1 liter you will have only nearly 25 to 50 milligram. So nearly 10 times less ions, okay. But what extra they have some bacteria, they have some mud, all kind of things are there, junk things are there, that's why you are not drinking. But if you distill that one out, can it, this also distill out, this is the same water, because they are, when you distill them, inorganic ions remains in the first pot. When you distill out, it comes only the water molecule. Okay, when you drink it, and you will feel you are fine, but actually you are depriving body by drinking distilled water. They are not good water. So more you distill, more you are actually making them less I mean rich of ions, and it will become non-ionized water, and they are not good for your body. You need ions for your body. Okay. So now point is that, so you understand that we in the water, for our survival we need both. So in magnetic moment here, if you are measuring the only EPR magnetic momentum, it gives you about the magnetic momentum and something, but magnetic measurements cannot give you the fine energy levels in the molecule. Okay. So for example, if I see a village from a train, okay, far after there is a field, and after this one, and I see that almost like trees are all connected, and houses are very different, they have a distance, but you will feel like they are connected. So it's like that. So when you see something very far, resolution is not very high, and your eye, they will feel like they are all connected. So you cannot really find the exact distance between the houses or between the trees. And if when you do the similar thing, when you go closer or take a micro like a telescope or a binocular, you can see them with far. So this is the difference in magnetic measurement. It's like seeing the village from the train, passing train, and from far. When you take EPR spectroscopy, okay, and different temperature, you can actually, it's like zooming in and trying to get exact distance between the houses and the trees. Okay, how does it matter? Yes, it matters. So those fine energy difference actually create a lot of actually control and exciting features they bring, which alone magnetic measurements cannot explain. Okay, so now suppose if you have, okay, so you know Curie law, right? Curie law said chi t equal to, okay, chi n t equal to C. Okay, so Curie law says that for a paramagnetic ion, this will be constant, and it will be whatever you do, chi and temperature multiply is like P equal to nRT, right? And if you have, so if you know P V equal to nRT, right? So P is pressure, V is the volume at that pressure, N is the, this is a small n or a capital N? Small n, number of moles, right? So you can take 1 mole, R is constant, gas constant, T is temperature. So at one temperature this is fixed. So whatever you do, if you pressurized, volume will decrease, because both has to, if you increase the pressure, volume has to decrease, or if you increase the volume, pressure has to decrease, right? So that this is always constant. Okay. So it is like chi and T are having the same relationship, and if you plot, this is a chi and this is T, they are like a hyperbola, like a PV plot, P and V plot. Okay. So they will come like this. At low temperature this will be increasing, because at low temperature close to 0, T become very small, chi has to be very big. At some distance after range, chi and T, their values are actually very close to each other, but moment you come close to 0 of T, then chi has to increase a lot to make this is constant. Okay. Similarly PV equal to this, if you go to very low pressure, okay, the volume will be booming. So if you take a drop of water in the space, okay, where nothing is there, it will blast into pieces and or into molecules. Okay. Hydrogen oxygen bond will not break, but the intermolecular forces are not that strong to hold them hold them together like you have in your bottle, in your body, it will just blast out. So if we are going outside the space, in the space like this, I will tear out everything, nothing will be there in the body, most of the parts will be just coming out by blasting. Okay, because you have outside you have no pressure, and inside you have a intermolecular forces, and their repulsions and all are there, and this hold by the atomic pressure. Okay, so that's the case. So if you don't want to feel it, so when you visit our laboratory, we have vacuum pump and the pipe, put your finger, in the pipe and apply the vacuum, you see it will suck your all muscle and all, and that pressure is nothing to, not that high like in the space. So you can imagine, if you go to the space, they will water molecules, gas molecules all come out. Okay. So similarly, that means at very low like pressure, volume is going to be huge. Okay. Now similarly, at very low temperature, this P scale and these are actually similar scale. Okay. And I am comparing here, the scale is like a V. Okay. So when you go to very low temperature pressure, volume becomes very high. Similarly, when you go to very low temperature, the chi becomes very high, so that their product is constant. So now if you have a chi t same plot, and you instead of what you do, take each temperature, so you have a T1 chi 1, T2 chi 2, like that you will go till this 300 to 295, like that 2 Kelvin. Every temperature corresponding chi will be different. Okay. So if you multiply 1, it will become chi 1, T1, chi 2, T2, like that it will continue. So you are getting, instead of this plot, now this correspond to this, and that is my plot here. Okay. So now if you have taken this chi and corresponding T, so this is T1, this is chi 1, this is T2, chi 2. So when you do it here for a for copper 2 ions and it is not interacting with each other, it will come like 375. No, it will come like this. So this is the value 0.375 here, and it constant. Whatever you do to the temperature, nothing change. Okay. So when you come also here, no change, because their multiplication is constant. This is suppose T at 2 Kelvin. Okay, you see, if you go to 0, it will be bump up to the infinity. Okay, because this is going to be bottom and it is going to be 0, and something multiplied by 0 is value and it cannot be determined. Okay. Now, so I supposed to get a value like this, but experimentally if you measure, it will come like this, and after some times it will be decreasing a little bit here. So now this decrease you can actually due to the some effect. Intermolecular interactions between this copper 2 and sulfur, you go to very low temperature, they will start magnetic interaction, dipole interaction through space. So they are like in tiny magnetic needles. Okay, they will be feeling each other because their thermal motions are not there, and they will feel them. Okay. So it's like keeping two enemies in a room, and after some time they are friends. Okay. And suppose the time and the empty room is actually the kind of temperature. Okay. So now if you take nickel 2 plus ion, this is the case will come where its value actually nearly 1, and you also supposed to get like this. Okay. But problem happens, it will not come like this, it will come like this. Okay, 2 ions are not interacting, and after some time it will be like this. Okay. So why this fall starts? This is due to the zero field splitting of the nickel 2 ion. So now you say, what's the zero field splitting? Zero field splitting says that if you do not apply a field, and if you have you have more than one electrons in a center, and they will repel each other and they split the energy lines. So the separation they will bring, they call zero field splitting. So due to the intermolecular interaction, inter-electron interaction, repulsion, they split the energy levels, and they will produce further energy levels, and then their Boltzmann distribution will start, and then they will start organizing, and this will be the fall. But this one you cannot really value how much zero field splitting energy you cannot get exactly from the magnetic measurement, because this is a mostly powder average. So what you do, the same complex you can measure EPR spectroscopy, you can get their EPR signal. If you feed them, model them, you get exact value, but from this one you cannot. So this is the limitation of magnetic measurement, where the curve cannot produce exact value of the D parameter and a G parameter. Any combination of them, it will, okay, you can feed this curve. But what is exact D, exact G, exact E, all to bring, you can actually need EPR measurement. Okay. So you have studied EPR measurement a bit at all? No, right? Studied. Okay, some says that they have studied. Let's see how much you have studied. You have studied. How many have you studied EPR spectroscopy? Raise your hand. Only 1, 2, 3, 4. Okay, 6, 7, 8. Okay. So 1/3 of the students, they have studied EPR spectroscopy. Okay. How many classes? Fully on EPR. Unit. So how many classes nearly? 8 class. 6 to 8 classes. So I take 7 classes. Okay. 7 classes are a lot. Okay. So okay. Now let's see. I lecture on this EPR spectroscopy and see whether they are the same or how much they are different. Okay. So you have seen the moon, one side of the moon. Did you see the other side of the moon? Or ISRO tried to land 2 times? No. Do you know to the other side? You don't know where or ISRO tried to land and last time landed? Yes, it's the other side where it is more rough and more mountains, more craters and what do you call it? So the moons are looking nice when you are romantic, but when you are sitting with a telescope and want to see what's moon and go to ISRO, you will see moon is not looking like this. Moon is looking very rocky and full of heats all around. That's why looking black. Those are all asteroid hits. Okay. So now when they try to land there, they are not so successful. Okay, most of the time they crash out. Okay. Now EPR spectroscopy, let's see how much you see both sides of the moon. Okay. Now what's EPR spectroscopy? It's like NMR spectroscopy, and it is nearly similar time they develop. I think there was a only 4 years difference between these two spectroscopy. Principle is same. So what is the principle says? Then in EPR we try to see electronic transition coupled with nucleus or only electronic. Okay. In NMR we see the effect of the electronics environment, but we are probing the nucleus. So in the NMR spectroscopy always we are measuring the nuclear energy differences and their positions, and from there we are predicting characterizing them. Okay. So what happens when you have a NMR spectroscopy? Suppose here the tiny nucleus and electrons are here. Depending upon your number of bonds or whatever, this is electrons. I told you they can go closer or go far, or they can deform depending upon how you make the bond. Okay, and how many bonds and all. So now this is electron density is like a balloon. Okay, so you can imagine a balloon and you start quizzing away anyway in a play mood. If you don't have time, you give it to a kid and ask that kid to play with the balloon, and you see what all the way the kids is playing, how the shapes are changing. You watch and feel that this is the similar way, all possible way we actually deform the electron density around metal center or at any atomic center when we make bonds on any complex. And time, if compound to compound, their distribution around the nucleus is changing. If it is not changed, remain same for the same carbon atom, it will remain the positions of the chemical state value are same. For aromatic carbon, it is coming 130 ppm. For in methane, it will come nearly maybe 10 ppm. Same carbon atom. How did you change to so much? Because you said hybridization, carbon-carbon bonds, all are, that means what? Electron densities are not same around the nucleus. So nucleus is feeling that my electrons is array or deform, whatever the way it is feeling, and they are changing in the nucleus energy levels. Right? That is what we are proving. So it is going to more deshielded or more shielded. That's what we are studying, right? And we say that these are the range already established for this kind of compound. This is this, this is this. We just correlate. Okay. Fine. So now, the EPR spectroscopy, the nuclear spectroscopy NMR speaks about the electronic change and the environment change and their effect on the nucleus. So you are probing nucleus, and why? Because of the electronic environment. Okay, this is changing, and this you are probing. Here you are probing. Okay, now in the EPR, what we are doing? We have a same nucleus, same electron. Now we are trying to probe here and see its own effect, and also through coupling. EPR spectroscopy is not without the nucleus effect, okay, and you see the both, okay. It's like if you heat here, you will only not hit your skin, also you will hit your bone, okay. If you hit here, only you will hit mostly on your muscle, not at your bone, because bone is too far. But when you hit here, you cannot really resist on the skin. So these two are like that, but you have effect. Okay. Now point is that uh, here the energy levels are higher, separation is higher, and you need microwave. Okay. Here energy difference is smaller, you need radio wave. Why you need this wave? Because what we do all the time, we here the electronic energy level, E energy levels we split, okay. Also it is coupled with the nucleus, they will further split. Here we are effecting only seeing on the nucleus and their separation, okay. But this in nuclear energy levels are separations are smaller, that's why you need this is lower, so this is equivalent to h nu, so nu will be smaller when the energy difference is smaller. Here it is higher, so nu 1, and if it is nu 2, h is same, so nu h is same, Planck constant, and nu 1 is always greater than nu 2, okay. So this is, and that's why EPR is very sensitive than the NMR, okay. So if you have a tiny amount of parametric ions like 0.1%, even 0.01%, impurity also can be sensed by the EPR, but NMR you need always lot of samples and longer time you need to measure, okay, because of the sensitivity issues of this population difference, that Boltzmann difference. Here difference is so less that it is both are nearly same populated, tiny difference in population, and that's why signal intensity is very small. Here difference can be huge, and then you just need its sensitivity is higher, okay, sentiment of the molecule, in that we have to read, okay, fine. So now if I want to measure how the things are, okay, so when you are measuring the tube you are using, in every lab you go, unless you get on an NMR tube that is made of actually quartz. Quartz, you know what is quartz? Are you using quartz today? Yes, your screen of your every mobile, this is a quartz, one kind of crystalline quartz. It has different phase, one of the phase, very hard one, okay. So SiO2 is not the glass you are using on the door, okay. This is silicate, it has mixture of potassium or sodium ions in it. So more potassium sodium ion in it, it is more brittle and easy to melt. The one you have, it will melt above 1000 degree, this will melt around 200 or 300 degree. Borosilicate will melt around 600 or 700 degree. So more covalent character you bring, their melting point increases. More ionic character you bring, they become easy to make, and these are very easy. You can buy it easy all, and they are easy to make. Okay, but so the NMR tube or EPR tube, NMR tube, the difference is that this tube is like this, and it is made of silica, okay, SiO2, and it costs around suppose 500 rupees per this one. EPR tube is similar way, bit longer, but bit narrower. They are not made the same way, but it is much more purity. Why? Because some amount of impurities you will have iron or something, it will always give you an EPR signal. So this has to be very highly pure, and there is the price increases. So one EPR tube can cost you 25 to 30,000. Can you imagine? So this is the difference. One NMR tube, if you break, you only cost 500 rupees. But one EPR tube, if you break, how many NMR tube can you buy? Can you imagine? 60 or something? 30,000 is how much? Around 60 EPR tube you have to buy, right? So that much you are breaking by mistake. Okay. Why you need to have? Because it has to be impurity free, and this impurity actually they has to be from the glass glass. So when they make it, they purify the glass in a way they are not showing any signal due to the tube. Okay. Here they are actually are okay, because you mostly need the spin active nucleus, and spin active nucleus are less, and also their sensitivity is low. Okay, this is the problem point. Okay. Okay, so both can be measured in the solid state or liquid state, both on different temperature, all can be done. So I can measure the EPR at different temperature, in different solvents, solid state, liquid, or in solution, wherever I want. NMR also beat up like that. Or solid state EPR NMR, when they do, the rotor has to rotate very fast, so that for the machine it feels like a liquid. Okay, so they have a magic angle, and you do that, you have to rotate. Okay. So now it is the logistics I am just talking. Now let's go to the EPR spectroscopy now. Okay. So now if you go to EPR spectroscopy, now see that I just can I take a box, and in the box I take all the gas molecules away, and I only put one free electrons. Okay, one electron, free electron. Now this electron is traveling anywhere, and then it has a, if I apply magnetic field, the electron will be parallel to the magnetic field. Okay, but it also can be also rotate, go like opposite to the applied magnetic field. So it can have two orientations. So I just now come to the point. So we have S equal to half for one free electron. Okay, free electron. Now moment you apply here is equal to 0. Okay. Now moment you apply a magnetic field is equal to non-zero, then this will be no longer S. It will be S will be there. S will be split into two state, MS state. Okay. So how the MS states are there? MS state will be from minus S to plus S. Okay. Fine. So for half it will be difference, always this difference will be step will be by 1. Okay. So always 1 1 1 it will go. So it will become minus half and then plus half. Okay. So if I have a S equal to 1, similarly it will go to minus S to plus this, it will become minus 1 0 and plus 1. These are the thing. And for the half it will be minus half and plus half, right? And so on for every ion. If you have the way your Riemann splittings are there, you get the energy levels. Okay. Okay. So electrons will be having a state which is minus half. This is the MS state. Don't talk about them anymore. State, yes, they are MS. Okay, quantum state, and then it will be having plus half. Okay, so if it is a spin of like this here, the same electron will be here in the opposite way. Okay, so now the half means the magnitude, and plus and minus will mean that orientation. So if it is electron is parallel to my magnetic field, it is plus half. It is the electron is opposite to my orienting, my opposite to my applied magnetic field, it is a minus half. So plus and minus, it is the direction of the with respect to the axis. Suppose you have the z axis, plus along the direction, plus up, plus sign, along the bottom towards the down, it will be minus. Very remember this. That's how the symbols and signs are coming, and their magnitude is same. Okay. So if you find a magnetic momentum for the both the orientation, it is the same. If you apply, take a 10 milligram of copper 2 plus ion, and then apply magnetic field in this direction, measure magnetic momentum, and then you reverse the field, again measure it, you get the same value identical. Okay. So its magnetism will be same, but you can how you orient it only can change. Okay. But when they try the electrons with respect to each other, they take such rotation or orientation, that is different. So now what I say that the yesterday I have told you copper 2 plus ion, that is the one with the acetate OSC 4 times 2 water here. This one, these electrons inside like this mostly, and they are randomized like this. This is when you apply the field, it is not changing. These orientations are not changing. That's the point, remember that. So you cannot flip them by this. If you flip them, that is also possible in some molecules, that is called different phenomena, but not happening in the copper acetate. You are not flipping the spin, we apply the magnetic field. A magnetic field is only to make them to probe them, but not to disturb them a lot. You disturb a little, part of them little, but not you change their orientation. Okay, this is the difference you have to see. So when you are applying magnetic field, as the field is trying to keep one towards its direction, then see others are how they are oriented. Okay, so what I try to say that here when you are in EPR, what we are doing, you are the same spin, this one, this state, you will get no signal whatever you do. These spins are not going to, if this one flips to this side, this will flip to the other side. So if you think that you are applying magnetic field, this is going to this side, then this will flip to the other side. So the overall state always is equal to 0. Okay. So for this spin, it can never be actually you can get signal, because it's a diamagnetic state, it will not give any EPR. Okay. For criteria to be EPR active, it should have at least one unpaired electron. More is fine, but at least one. Okay. Now for this state, this is a state on applied magnetic field, and you can change, tilting angle can change, and even you can make parallel depending on how much random and how much which temperature you are measuring. Okay. So for copper acetate, you will get a room temperature EPR signal because of this random state orientation. For the one, if you go to some temperature, so I have said that if you go to suppose 150 degrees centigrade, okay. So now let me draw. This is the chi T, okay, and this is the H and the M. So this is the magnetization, this is the field, okay, and the temperature and the chi T. Now I said that it was coming like this. Now here you get EPR signal because of this state, and this state is very little. But more you go here, it is having both, okay, this and this. So the species which is in this state, it will give EPR signal, but not the species which are actually having this kind of organization, they will not give EPR signal, because the electrons are entangled and they will not able to undergo transition like the way I want, and only this can do. Okay. So I get EPR signal for this one, but not for. But now if I go to here, this temperature, suppose this is 10 Kelvin, okay, and my here is complete diamagnetic, that means this is no longer populated, all are in this state. So the same amount sample, same thing you have kept, when you went to the 2 Kelvin or 10 Kelvin, there is no EPR signal. Why? Because all the molecules, they have populated to the diamagnetic spin ground state is equal to 0. Yes, it's same. One we call it parametric resonance, and another we call it spin resonance. It's the same. Okay. So now you understand that you can probe it that it is a diamagnetic state also by the EPR, and the kite is changing. Also you get a signal intensity also will change. Okay. There you can also probe them. So EPR spectroscopy is complementary to the NMR magnetic measurement. Now go to nickel 2 plus ion, where you have a zero field splitting. So what is a zero field splitting? So now I said that so you got a EPR, you have this as a transition thing, and then you apply magnetic field, they go increase. So more you apply the field, they'll split up. So what they have, you go with a sample, they will put in the machine, and then someone will sit in the machine here, they will give command and they will first tune the sample. What is the tuning? They have a box like things, and in the box it produces a microwave. So microwave energy they will fix it. So that means nu is fixed, nu, H nu, that nu frequency is fixed. Now what they will do? They will sweep the field. Now when they start the button, this magnetic field will start with 0, then slowly increase. Okay, in our machine it can go to 1.2 Tesla here in IIT Madras. Okay, so now it will keep on varying, and when it is somewhere here, no signal, and then somewhere you get a signal like this, and then again no signal, and then whatever you go, nothing. So you got a signal, and that is due to the this one is going to the here, or this is coming back here, and that's the signal you get, which will match with the frequency. So because if you change the frequency, again it will match, but in the different field. So frequency is tunable little bit. Okay, so it is around 9.5 gigahertz, but not exactly 9.5. So sometimes you are tuning, it is 9.48 gigahertz, and then next time you are tuning, it may be 9.42 gigahertz. Next time you are tuning, maybe 9.5951 gigahertz. So when you tune, slightly the frequency changes. This will be going to this side or that side of the field. So field will be taking less or more, depending upon what frequency you are actually trying to match. So this is going to be like this, and your frequency can fit here or here, according the field will be, the scale will come. So EPR comes like this. Here is the field H or B we call it, and is the intensity I. So in the EPR we don't care about the intensity, we only care about the signal. So it go like this and come like this. Okay. Now in NMR what we get, it is, this is the first derivative. Okay. So this is the first derivative. Okay, something. And in NMR we are not taking the first derivative, we are taking the Gaussian plot. Here also it comes like this, but we take the first derivative, that's why it comes like this. So this part, due to the here to here transition, and the other side of this up here to here transition. Okay, so this is the side. So if you derivative this, slope is slowly increasing, that's why slope is increasing, and there comes a point here where slope is actually becomes 0, and then it's slowly falling. So this is the part we get. So this is the derivative plot, that's why you look like this. EPR is like an MR, but is a derivative, first derivative plot, that's why it look like this. Okay. Why you take derivative? You can also take that the shape also, but when you take derivative, we get multiple features, and there we can speak about their hyperfine energy levels. In NMR we are not dealing about their hyperfine energy levels. Okay, and this is the aim of EPR spectroscopy. These hyperfine energy levels only the most important things to deal with, and then analyze, and their values are important. Okay. So what you call it, this coupling between the nucleus you are getting directly. Here you have a nucleus electron interaction we can get from the hyperfine lines. Okay. Now you get like this, so you need to tune it and you get it here. Now if you go to NIC, for this one, if you get the other one I said, copper 2 plus, 2 of them are there, O acetate 2 times azide, and water molecule again. The second compound I wrote, I said this is ferromagnetic and this was antiferromagnetic, right. Now when you are cooling this sample, it was going to this state, on the other case it will go to this state. So it had this plus this, for this compound it will have this, not this one, this. So this is the most population, because this is the on cooling, this is going to be populated the reverse way I said yesterday, if you remember the curve. So the kinetic curve was like this. So for copper acetate it was like this, falling, like this, and for the other one maybe it was going like this. So when you have ferromagnetic coupling, that time EPR intensity will be coming stronger and stronger, because you are populating the state which is actually two spins are parallel. Now there is a feature what is distinct between these two. Okay, what is that? When you make this one for this compound, you get a signal around G equal to 2, okay, no other signal. But moment you go to this compound and it will give a signal similar at the same place, okay, sorry, if you go like this and a signal like this, it will go and go, and then here will be a small signal. So you see the difference? For this compound you have an extra signal and it has a one signal. So now why there are two signals? I can by looking at the EPR spectroscopy, I can tell it's a dinuclear compound, whether ferromagnnetic couple or antiferromagnnetic couple. How? Because when you have this one, this is coming delta m is equal to plus minus 2, and this signal is coming delta m is equal to plus minus 1. Okay. Because this is mostly coming from the one copper ion center and their interactions are very not weak, and that is not coming here. But here when the signal will be, they are coupled together, for this state it is this signal and these signals are coming, and for this state no signal coming. So for the, you can see when the couple completely cancel each other, no signal, but for this one you have the two signals will come. So now what is that? So now if you take the EPR spectroscopy, it has HNU, this HNU difference, okay, HNU equal to, this is a multiplication of G, the applied field, and MS, and then beta and some things are here, okay. So it is something, so if you G is actually fixed, B actually also magnetic field, and then MS actually, and then beta and others are there. Now if you take if you have to take difference here, which will be coming H delta nu, okay, difference, okay, and then that time will be G is the same, B will be the same, and it will become delta MS, and this beta and all will be there. So between these two states, this difference will be coming in the delta MS. So now this delta M is actually the one for the half spin. You can see this difference between these two is 1, minus half and plus half, the difference is 1. But moment you go to nickel ion, between this and this, or this and this, difference is actually also minus 1. So you get a signal here. The other one for minus 1 to plus 1, you get a signal is delta M is equal to plus, this is 2. See, the difference is 2. So here you get the signal. So this is called forbidden transition, and this is allowed transition. And this always comes at a low temperature and weak in intensity, because this is forbidden in nature. And that is the difference for a triplet species. Any triplet species having two electrons parallel to each other will produce a signal at the field half of this. So if it is H1, this will be H1 by 2. So suppose I get a signal, this one H1 equal to 3400 Gauss, this signal will come H1 by 2 will be around 1600 Gauss, okay. So this signal will be weak, is a small signal, this is a huge signal. So these are the two signals you have seen. So EPR spectroscopy can tell me that is a singlet species and triplet species. So if you have an organic radical, one radical center is there, it will not produce a signal here, only produce a signal here because of this transition. But moment you have this what you call it, triplet species, it will split into 3 states. So 0, plus 1 and minus 1. The transition between here to here, the one will give this one, here to here or here to here will be giving this signal, okay. So that is what actually difference between a singlet species and triplet species. Now you have to see them only at a right condition, that is a temperature you have to control where you can see it. Triplet species, always most of the cases their signals are seen at the lower temperature and not at the higher temperature, because the intensity can be so noisy, they can be in the noise level. To get a sharp intensity, you have to cool the sample. This is a condition, okay. So done. So you have understood that I can distinguish between these two states, whether it is coupling in nature, but EPR spectroscopy cannot give you the J value. It cannot give you the J value. The J value is cannot come. It will can give you the nature of the state, okay, like which spin state, and it can give you other parameters like now D and E. Okay, take 5 minutes break. I will go to another episode of the EPR spectroscopy.
SwayamPrabha, Digital India, Educated India.